Hello friends, welcome to my lecture on general linear programming problem. In our previous two lectures on linear programming, we solved a linear programming problem involving exactly two variables by graphical method. But if the number of variables in the linear programming problem are 3 or more than 3, then the graphical method cannot be used, because even for the case where a linear programming problem involves exactly 3 variables, it will be difficult to solve it by the graphical method. And so, what we will do is we will consider a general linear programming problem involving say n variables, where n is greater than or equal to 2, okay, and then we will solve it by simplex method, which is very well known method to solve a linear programming problem involving n variables. So, let us discuss what is a general linear programming problem. Any LPP, any linear programming problem involving more than 2 variables, may be expressed as z equal to C1 x1 plus C2 x2 plus Cn xn. Our objective, which is our objective function, and we want to maximize or minimize this objective function subject to the constants a11 x1 plus a12 x2 plus a1n xn less than or equal to b1, a21 x1 plus a22 x2 and so on, a2n xn less than or equal to b2 and so on, am1 x1 plus am2 x2 plus and so on, amn xn less than or equal to bm. And the non-negativity restrictions on the variables x1, x2, xn are that they are all non-negative. Now, well, let us define a solution, a set of values x1, x2, xn which satisfies the constraints of the LPP. Constraints of the LPP means these inequalities, a set of values of x1, x2, xn which satisfies these m constants, okay, is called a solution of LPP, is called a solution of LPP, any solution to a LPP which satisfies the non-negativity restrictions. Now, suppose our solution of LPP is such that it also satisfies these non-negativity restrictions x1, x2, xn greater than or equal to 0, then we call the solution to be a feasible solution of LPP. Now, any feasible solution which maximizes or minimizes the objective function of the LPP is called an optimal solution. Okay. So, if any feasible solution we have which maximizes or minimizes the objective function z equal to C1 x1 plus C2 x2 and so on Cn xn, then it will be called as its optimal solution. Some of the constants in equations 2, some of the constants here in equation 2 may be equalities, some others may be inequalities of less than or equal to type, and remaining ones inequalities of greater than or equal to type. The inequality constants are changed into equalities by adding or subtracting non-negative variables to or from the left side of such constants. Okay. If the inequality is less than or equal to type, then we will add non-negative variables, okay, to the left side, and if the inequalities are of greater than or equal to type, then we will subtract non-negative variables from the left side of such constants. So, let us now define slack variables. If the constants of a general LPP be say sigma j equal to 1 to n, aij xj less than or equal to bi, I equal to 1 to k. So, you can see there are k equations, because when I is equal to 1, you get the first inequality as a11 x1 plus a12 x2 and so on, a1n xn less than or equal to b1. Okay. The second one is a21 x1 plus a22 x2 and so on, a2n xn less than or equal to b2 and so on, ak1 x1 plus ak2 x2 and so on, akn xn less than or equal to b k. So, suppose there are k inequalities which are of type less than or equal to, okay, given by these k equations, okay, sigma j equal to 1 to n a I j x j less than or equal to b I, where I is taking values from 1 to k, then the non-negative variables S I, because these are less than or equal to type, and when the inequalities are of less than or equal to type, we add non-negative variables to the left side of such constants to make them equalities. So, we add S I, okay, to the ith equation here, which is a I 1 x 1 plus a I 2 x 2 and so on a I n x n less than or equal to b I, we add non-negative variable S I. Okay. So, S I is added to the ith equation to convert it into an equality. Ith equation is a I 1 x 1 plus a I 2 x 2 and so on a I n x n less than or equal to b I. To convert it into an equality, we add S I to this, non-negative variable S I to this. Okay. So, this gives us a I 1 x 1 plus a I 2 x 2 and so on a I n x n plus S I equal to b I, and this we do for all I equal to 1 to k. So, we get the equality sigma j equal to 1 to n a I j x I j a I j x j plus S I equal to b I equal to 1 to k, and these non-negative variables S I's are called slack variables. So, slack variables are those which are added to an inequality of type less than or equal to convert it into a equality. Now, let us go to next possibility. If the constants of a general LPP be of the type sigma j equal to 1 to n a I j x j greater than or equal to b I, okay, where I takes values k, k plus 1, k plus 2 and so on, okay, then what we will do? We will subtract non-negative variables from the left side, okay, of this a constant to convert into a equality. So, sigma j equal to 1 to n a I j x j minus S I equal to b I. So, sigma j equal to 1 to n a I j x j minus S I b equal to b I, where with this S I non-negative variables S I are called surplus variables. So, this we do for every I. These S I's are called surplus variables. Now, let us discuss the two forms of LPP. They are canonical form and standard form. After the formulation of LPP, the next step is to obtain its solution. But before any method is used to find its solution, the problem must be presented in a suitable form. Now, what are those suitable forms? One form is one form is a canonical form, the other form is a standard form. Let us define what do we mean by a canonical form and a standard form. Now, let us first take the canonical form. The general linear programming problem can always be expressed in the following form: maximize z equal to c 1 x 1 plus c 2 x 2 plus and so on c n x n, subject to the constants a I 1 x 1 plus a I 2 x 2 and so on a I n x n less than or equal to b I equal to 1 to m. So, there are m constants here, okay, given by the m inequalities which are of less than or equal to type, and x 1 x 2 x n are non-negative variables. So, non-negativity restriction is there on x 1 x 2 x n. Now, so this general linear programming problem can be expressed. Now, suppose a constant is of greater than or equal to type, okay, greater than or equal to type instead of less than or equal to type, then we multiply that constant by -1 and bring here instead of greater than or equal to less than or equal to. Say for example, say a certain equation a k 1 x 1 plus a k 2 x 2 and so on a k n x n greater than or equal to b k is there, okay, in the LPP, then we will write it as minus a k 1 x 1 minus a k 2 x 2 and so on minus a k n x n less than or equal to minus b k. So, all the constants, okay, will have to be brought in the form less than or equal to. If there is any one which is greater than or equal to, then we multiply by minus 1, okay, the whole inequality and bring it to form less than or equal to. And now here the objective function, if it is if we are given that you minimize z equal to c 1 x 1 plus c 2 x 2 and so on c n x n. Then equivalently we can write it as maximize, we convert it into the form maximize z dash equal to minus z, okay. So, that is equal to minus c 1 x 1 minus c 2 x 2 and so on minus c n x n, okay. So, if there is a minimization problem, we have to minimize the objective function, then for that we consider the corresponding maximization of z dash equal to minus z dash equal to minus z, okay, which is minus c 1 x 1 minus c 2 x 2 and so on minus c n x n, and get the and bring the LPP in the form maximization of z equal to c 1 x 1 plus c 2 x 2 and so on c n x n, and all the constants have to be are brought in the form less than or equal to x 1 x 2 x n greater than or equal to 0 is already given to us. Now, so by that is what we say, by making some elementary transformations the LPP can always be brought into this form. This form of LPP is called as the canonical form, and it has the following characteristics. What are the characteristics of this canonical form? First thing is that objective function is of maximization type, okay. Objective function is of maximization type. If it is not of maximization type in the LPP, then we have to bring it to the form of maximization, like considering maximization of z dash equal to minus z. Now, all constants are of less than or equal to type, all constants must be of less than or equal to type, all variables x I are non-negative. So, all the variables x I are non-negative. The canonical form is a format for an LPP which will find its use in the duality theory. When we will consider duality theory, there we will see that this form of LPP, which is called canonical form of LPP, it is a format for the duality theory. In the case of linear programming problem, it is a format in the case of duality theory. Now, the second one is standard form. The general linear programming problem can also be put in the form maximization of z equal to c 1 x 1 plus c 2 x 2 and so on c n x n subject to the constants a I 1 x 1 plus a I 2 x 2 and so on a I n x n equal to b I, where I is equal to 1 2 and so on up to m, and x 1 x 2 x n are greater than or equal to 0. So, here the constants are all of equality type, okay. We have a I 1 plus x 1 plus a I 2 x 2 and so on a I n x n equal to v I. So, we are given n equation m equations here, there must be m equations and the objective function must be of maximization type. So, this form of the LPP is called its standard form, and it has the following characteristics. Now, standard form of LPP we will discuss when we use simplex method to solve a general linear programming problem. In the simplex method, first thing that we do is we bring the LPP into the standard form. So, by bringing that into the standard form means if the function z, if the objective function z is to be minimized, we will consider the corresponding problem where maximization of z dash equal to minus z we will consider. So, maximization of minus z we will find. So, so first thing is that objective function must be maximized, and moreover that the equations m equations are there, okay, equality type, okay. So, if the constants in the general linear programming problem are less than or equal to or greater than or equal to, then by adding in the case of less than or equal to, by adding the slack variables, and in the case of your greater than or equal to, subtracting the surplus variables from the left side, we will be converting them to equality equations, into equations with equality sign. So, so there are m equations with equality here. Okay. So, so all constants are expressed as equations, okay, and right hand side of each constant. Now, this is very important, right hand side of each constant must be non-negative, that is bi has to be non-negative. Okay. So, bi if it is non-negative, we multiply the equation by -1 and bring the right hand side where and bring it to the side, bring it to the form where the right hand side is non-negative, and all variables must be non-negative. So, when we have here less than or equal to constant of less than or equal to type, we are adding slack variables S1, S2 and so on, which are greater than or equal to 0, and when we have greater than or equal to type here in the constant, then we are subtracting surplus variable S1, S2 and so on, which are again non-negative. Okay. So, first thing is that objective function must be of maximization type, all constants must be equations. Third thing is right hand side must be non-negative of each constant, and fourth is all variables must be non-negative. Now, for example, let us convert the following LPP to the standard form. We have here the objective function z equal to 3x1 plus 5x2 plus 7x3, and we want to maximize this, and the constants are 6x1 minus 4x2 less than or equal to 5, 3x1 plus 2x2 plus 5x3 greater than or equal to 11, 4x1 plus 3x3 less than or equal to 2, and x1 x2 are non-negative. Now, we are given the restrictions on x1 x2, okay, while the third variable x1 x2 are given to be non-negative, but the third variable is unrestricted, there is no restriction on the third variable x3. So, how we will convert it into the this LPP into the standard form? What we will do, since x3 is unrestricted, let us put x3 equal to x3 dash minus x3 double dash. We can always write x3 in the form x3 dash minus x3 double dash, where x3 dash and x3 double dash are both greater than or equal to 0. Now, the given constant can be expressed as, so with x3 equal to x3 dash minus x3 double dash, what we will have, the new constants will be of the type 6x1, this is unaffected because there is no x3 here. So, 6x1 minus 4x2 less than or equal to 5, that is the first constant. Second constant is 3x1 plus 2x2 plus 5x3 greater than or equal to 11. So, x3 we put as x3 dash minus x3 double dash, and we get 3x1 plus 2x2 plus 5x3 dash minus 5x3 double dash greater than or equal to 11, and the third constant is 4x1 plus 3x3 less than or equal to 2. So, here we get 4x1 plus 3x3 dash minus 3x3 double dash less than or equal to 2, and here all the variables x1, x2, x3 dash, x3 double dash are greater than or equal to 0. So, now we can see this problem LPP, the original problem, general linear programming problem, we have brought into the form where we have objective function is to be maximized. Second thing, all the constants, okay, 6x, all the constants are expressed, we have to express them into equations. Okay. So, this has to be expressed into equations, it is not still into the standard form, we just have observed that x3 is unrestricted. So, x3 can be written as x3 dash minus x3 double dash. We have converted the, we have written the constants in the form of variables x1, x2, x3 dash, x3 double dash, where they are all non-negative. Now, let us convert them into equations. So, since this is less than or equal to 5, we will have to add a surplus, we will have to add a slack variable there. So, 6x1 minus 4x2 plus s1 equal to 5, okay, where s1 is a slack variable. Now, here we have greater than or equal to, so we will subtract a surplus variable. So, 3x1 plus 2x2 plus 5x3 dash minus 5x3 double dash minus s2 equal to 11. Okay. Now, here again it is less than or equal to type. So, 4x1 plus 3x3 dash plus minus 3x3 double dash, and we add slack variable x3 equal to 2. Okay. So, with the help of two slack variables s1, s3, and a surplus variable S2, we are able to convert the given constants into equations. So, we have this. Now, the introducing slack surplus variables, the problem is in standard form becomes maximization of z equal to, now z equal to we have 3 x 1 plus 5 x 2 plus 7 x 3, 7 x 3 means 7 x 3 dash minus 7 x 3 double dash, because x 3 equal to x 3 dash minus x 3 double dash, and subject to the equations 6 x 1 minus 4 x 2 plus s 1 equal to 5, this is this equation. Then 3 x 1 plus 2 x 2 plus 5 x 3 dash minus 5 x 3 double dash minus s 2 equal to 11. So, this is this equation. Okay. And then the third equation 4 x 1 plus 3 x 3 dash minus 3 x 3 double dash plus s 3 equal to 2, that is the third equation. Okay. And we have x 1 x 2 x 3 dash x 3 double dash s 1 s 2 s 3 all greater than or equal to 0. So, we can see all the characteristics of the standard form of the LPP are there. Objective function is of maximization type, this objective function is of maximization type. Okay. All constants are expressed as equations, all constants are expressed as equations. Okay. Right hand side of each constant must be non-negative. Now, this is 5, this is 11, this is 2. So, right hand side of each constant is non-negative, all variables are non-negative. So, all variables x 1, x 2, x 3 dash, x 3 double dash, s 1, s 2, s 3 they are non-negative. So, the LPP, this LPP, okay, this LPP which has been brought into the standard form. So, this is the standard form of the LPP. Now, let us consider another example where we have to minimize the objective function z equal to 3 x 1 plus 4 x 2, and we are given the constants which are given in the form of equations 2 x 1 minus x 2 minus 3 x 3 equal to minus 4, 3 x 1 plus 5 x 2 plus x 4 equal to 10, x 1 minus 4 x 2 equal to 12, and x 1 x 3 x 4 greater than or equal to 0. Now, you can see here there is no restriction on the variable x 2. Okay. So, x 2 is unrestricted variable. Okay. So, here x 3 and moreover that we have in the objective function x 1 and x 2, x 3 x 4 are not there in the objective function. So, x 3 x 4 are slack oblique surplus variables. Okay. These variables x 1 x 2 which determine the minimum value of z are the decision variables. Okay. Now, x 2 is unrestricted. So, we can write x 2 equal to x 2 dash minus x 2 double dash, where x 2 dash and x 2 double dash are non-negative. Okay. Now, with x 2 equal to x 2 dash minus x 2 double dash, what we will have? We will, this problem will become minimum of z equal to 3 x 1, x 2 equal to x 2 dash minus x 2 double dash. So, 4 x 2 dash minus 4 x 2 double dash. Okay. And these equations will become 2 x 1 minus x 2 dash plus x 2 double dash minus 3 x 3 equal to minus 4, and 3 x 1 plus 5 x 2 dash minus 5 x 2 double dash plus x 4 equal to 10. Okay. And then x 1 minus 4 x 2 dash plus 4 x 2 double dash equal to 12. Okay. Now, right hand side of all the constants must be non-negative. Okay. But we notice here that first constant in the right hand side of the first constant we have non-negative, we have negative constant minus 4 is there. So, we multiply this first constant by minus 1 and bring it to the form minus 2 x 1 plus x 2 dash minus x 2 double dash plus 3 x 3 equal to 4. Okay. So, this first equation is modified in such a way that right hand side becomes plus 4. Okay. The second equation and third equation are okay, because the right hand side is already non-negative. The maximization of the minimization of z is given as the LPP. So, we convert it to maximization problem. So, maximization of z dash equal to minus z, that is minus 3 x 1 minus 4 plus 4 x 2 dash minus 4 x 2 double dash. Okay. This is how we convert this minimization of z to maximization of z dash. So, now we have maximization of minus 3 x 1 plus 4 x 2 dash minus 4 x 2 double dash subject to the constants. The constants are minus 2 x 1 plus x 2 dash minus x 2 double dash plus 3 x 3 equal to 4, that is one constant, and the other two are 3 x 1 plus 5 x 2 dash minus 5 x 2 double dash plus x 4 equal to 10 and x 1 minus 4 x 2 dash plus 4 x 2 double dash equal to 12. And we have x 1, x 2 dash, x 2 double dash, x 3, x 4 all non-negative. Okay. So, the problem has now been converted to the standard form, maximization of z dash equal to minus z, which is minus 3 x 1 minus 4 x 2 dash plus 4 x 2 double dash. The first constant is minus 2 x 1 plus x 2 dash minus x 2 double dash plus 3 x 3 equal to 4, this one, and then the second one is 3 x 1 plus 5 x 2 dash minus 5 x 2 double dash plus x 4 equal to 10. So, this is second one, and then x 1 minus 4 x 2 dash plus 4 x 2 double dash equal to 12, that is third. Okay. And all these variables are non-negative. So, the given problem has been brought into the standard form, and now we will proceed and solve it by using simplex method, which we will discuss in the next lecture. So, we have brought a general linear programming problem into the standard form, and we have seen how we can do that. Now, in the next lecture we shall discuss how to solve a general linear programming problem. We will bring it to the standard form and then use simplex method to solve that problem. With that, I will like to end this lecture. Thank you very much for your attention.